Welcome to Higher Computing for Everyone, Lesson 2.3, Patterns and Place Values of Binary, and also an introduction to hexadecimal. So earlier we went over the basics of binary, and I explained how a base 2 system is different from a base 10 system. I realize that some of this material might be difficult at first. Just take your time, and feel free to ask questions if you need to. Now, first of all, let's review the most important principles about binary. You might say that binary is how a computer counts, but this is only a small piece of the story. Binary is the way a computer represents all numbers and data, from simple counting to music files to movies or anything else. Now, when we show binary numbers, we will typically write the numbers with spaces after every 4 digits. So, for example, we wouldn't write a binary number like this. We would instead we would break it into 4s, starting from the right, and we would put a 0 if needed to make sure that the binary number is in sets of 4s, and then we would write it with a space, like this. There's 2 reasons why we do that. The first is it makes it easier to read the binary number. Then is that there is a number counting system that I'll show you soon called hexadecimal, and it is much easier to work with hexadecimal and binary if you write your binary numbers in sets of 4. So, given any binary number, let's just write one out here. So how would we, let's go a little bit more here. Okay, so in this example, we break it into 4s, and our first set of 4 binary digits is here. You can write that. And our next set of 4 is here, and since there's 3 digits, we need to add an extra 0 just to make it easier to read. It doesn't change the value at all. And that's how we would write the binary number. So now let's go ahead and look at a table real quick. If we start counting, this is of course 0, 1, 2. Now this should be very easy for you if you have already done the lesson immediately before this one. If not, then go back and load that lesson. Now, I'm doing this for a reason, which you'll see in just a second. And now we stop at 9 because I want to ask you a question. What do we put for the next number here if we want to express the next number as a single digit, like we've done with all of the numbers before? What do we do? Well, the answer is that once you run out of digits, we've used all the digits from 0 to 9, what we actually start doing is we start using letters. So instead of 10 being 1, 0, we actually say that 10 is A, and then 11 is B, 12 is C, then of course we have D, E, and F. Now, it is very important that you memorize this table. It's not that hard, and you should be able to write out from 0 to F, which is 0 to 15 in binary, using letters once you get past 9. So remember, A is 10, and F is 15, and it doesn't go any higher than F. This is called hexadecimal. Now, there's more to hexadecimal than what I've explained so far, but I want you to understand, first of all, how to convert any 4 binary numbers to hexadecimal. It's very easy. All you have to do is remember that up to 9, you just write the digit normally, 0 through 9. And then once you get past 9, you start using letters, A through F. You don't go any higher than F. Now, let's suppose that we have a binary number, and we want to convert that binary number to hexadecimal. Remember, hexadecimal is the counting system that allows you to count from 0 to 15 using a single digit, where we use 0 through 9, and then after that, we use A, B, C, D, E, and F. So if we want to convert this to hexadecimal, it's extremely easy because it's less than 10. So if it's less than 10, you just convert it to decimal, really. You don't have to do anything special. It's just 6. If it's more than 10, then what you have to do is realize how many more than 10 it is, and then you just have to remember the table. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Start by remembering that A is 10 and F is 15, and you'll start to remember the others fairly easily. So since 1100 means a 1 in the 8th place and a 1 in the 4th place, that's 12, and so we know that that is C. Now this is where a bit of the magic comes in, because when you have a binary number that is this, now think of this as a single binary number, and you want to convert that to hexadecimal, all you have to do is convert each 4 digits to hexadecimal. So the answer is going to be 6C. Now what you're going to find out is that the math actually works here, and I'll show that to you in a minute, but keep in mind for the time being that you can convert any 4 binary digits to hexadecimal even inside the same binary number. So even if we have a very large binary number, okay, so let's suppose we have this binary number. Now notice that I've written this out in sets of 4 binary digits because that'll make it easier to convert to hexadecimal. Now, in order to convert this to hexadecimal, all we have to do is convert 4 binary digits at a time. Now, the first set of 4 digits we know is just 4 plus 2, which is 6. And now, the next set of 4 digits is going to require us to remember our table, and we can just write it out real quick. We know that 10 is A, 11 is B, 12 is C, and then D, E, and finally F. So all we have to do is match this to the table, and we will see that we want E. And then the last number is very easy, it's just 1. So here we've converted the binary number to what it is in hexadecimal, which is 6E1. Okay, so now let's suppose that we have another binary number, which I will write out in a second. So let's suppose that we have this. Now think about this binary number, how hard it would be to convert it to decimal by looking at all of the different place values and adding them together. We would be saying there's a 1 in the 2's place, the 4's place, then we'd have to add all of these numbers together, which you certainly can do, but hexadecimal provides an easier way to do that. All we have to do is, first of all, convert this number into hexadecimal. We know that's 3, we know that's 7, we know that's 5, and we know that's 6. Now remember, you can only convert 4 binary digits to hexadecimal, not to decimal. So if you have a binary number like this, for example, and you're trying to convert it to decimal, you can't cut it into 4 and say it's 67. That's not true. It would be, in hexadecimal, it would be correct, but not in decimal. So back to our number up here, 3756 in hexadecimal. How do we convert this number into decimal? Well, that's what we're going to look at next. So let's go ahead and look at just the number 3756 and how we would convert that to decimal. So we're converting hexadecimal to decimal. What you have to remember is that you're going to have place values in hexadecimal that are similar to what you have in binary or in decimal, except it's going to work a bit differently, and I'll explain that here in a minute. Okay, so first of all, let's look at hexadecimal in terms of place values, just like we did with decimal and binary. So let's write a number in hexadecimal. Let's write 3A. Okay, how do we interpret this? If you remember, every counting system has a ones place, and then the next place next to the ones is always the base, whether it's base 2 or base 10, or in the case of hexadecimal, it's actually base 16. So what we're saying here is we have an A in the ones place, which is 10, and we have a 3 in the 16's place. And you could plug that into your calculator and you get 48. So the answer is 58. That's how you convert hexadecimal to decimal. Now let's look at a more complex example. Okay, so here we have a hexadecimal number, and what we need to do is look at the different place values. So I'm actually going to space this out more. Okay, so let's look at the different place values that we have here. We always start with the ones place, and then we have the base, whatever that is. In this case, it's the 16s. Now, every column is going to be the base times the column before it. So remember, in base 10, every column is 10 times bigger. In base 2, every column is 2 times bigger. In base 16, it's going to be 16 times bigger, which means the next column is going to be 16 times 16, which is 256. And just for simplification, I'll write out 256 like this. So what comes next? If you have 256, then what you need to remember is that the next column is going to be 16 times bigger than 256. And that means the next column is going to be 4,096. You can see these numbers get very quickly, very fast, but the number you're looking at, 2AD1, if we were to express the same number in binary, it would look like this. 2A, let's see, D1. So if you were looking at this in binary, you would say the 1's place, the 2's place, 4, 8, 16, 32, 64, 128, and then 256. Notice that the 256 place here corresponds to this. Notice that the 16 here corresponds to this. And of course you go 256, 512, 1024, 2048. What comes next? 4096, which corresponds here. So that's how it works. The math just happens to be that you're doing binary in shorthand when you do hexadecimal. So that allows you to work with larger binary numbers, and rather than having a huge stream of ones and zeros that you're trying to add together, you can express that in hexadecimal, and converting from hexadecimal to binary is extremely easy because you can do it for every digit. Okay, so now how do we actually do the math here? All right, it's not hard at all. We remember we have a 1 in the 1's place. We have a 13 in the 16's place, which means that's 13 times 16. We have a 10 in the 256 place, which is just, that's easy. And then we have a 2 in the 4096 place, which is 8192. So the next thing we have to do is just add these values together. So we'll go ahead and multiply 13 times 16, and we will get 208. And then all we have to do is add these values together, and we'll get 10,961. Now let's do the exact same thing in binary, just so that you can see that it works in exactly the same way. So what we're going to do here is, first we're going to convert it to binary one digit at a time. 2 is 0010. A is 1010. D, which is 13, is going to be 1101. And then 1 is going to be 0001. So let's add it up here. We're going to have a 1 in the 1's place. I'm just going to write it under here. So I'm going to say 1 plus. Then we have, and that takes care of that one. Then we have a 1 in the 16's place. And then we have a 1 in the 64's place. And in the 128 place. Nothing in the 256. A 1 in the 512's place. Nothing in the 1024. And then a 1 in the 2048 place. Nothing in the 4096 place. And then we have a 1 in the 8192 place. So if we add these values all together, we get 10,961. So you see it works in the exact same way, but I would argue that it's easier to do that in hexadecimal because you really only have to add 4 numbers together rather than potentially a dozen numbers. Okay, so What I hope you've learned in this lesson is, number one, that you can convert any binary number to hexadecimal by first taking the number you want to convert, breaking it into fours, adding any extra zeros to make sure that you have sets of fours, and then converting the individual sets of fours to hexadecimal, remembering that A is 10, 11 is B, and so on. Converting from hexadecimal back to binary is just as simple. All you have to do is take your binary number, write it out, or take your hexadecimal number, write it out in binary, remembering to use a set of 4, and then you're done. So every hexadecimal digit becomes 4 binary digits, and every 4 binary digits become hexadecimal. Then to convert hexadecimal to decimal, you just remember the place values you have. So we have A, which is 10 in the ones place, that means we have 10, and we have 2 in the 16s place, which means 32. We add it together and we get our answer. So there you go. Feel free to post any